Chapter 11 supplement, and this is on polymers of alkenes. The reason why this is such an important supplement is that there is such a huge branch of organic chemistry and chemistry that's made up of polymers that it's a disservice to not mention it here. So then your next question just might be, well, since it's not in the book per se, is this going to be on the test? The answer is yeah, it's going to be on the test because it's very important. And these are things that you have in your household and that you know of. So we like our practical application. So here we go. Now polymers, poly meaning poly meaning many, and mer meaning parts, they are large, repeating, long-chain molecules. They're found in nature, including cellulose in plants, starches in food, proteins, and DNA in the body. But quite often we think of polymers as synthetic man-made, such as polyethylene, polypropylene, polystyrene, Teflon, and nylon. A lot of the names are the old common names rather than the IUPAC naming, though. They are composed of many small repeating units called monomers, and they just hook all the monomers together, and then you get your polymer. So it is made from the reaction of many small alkenes. Now, in addition reactions, polymerization, small repeating units called monomers join to form a long-chain polymer in an addition reaction. So ethylene is one of the basic building blocks for these addition reactions. Now, I use the word ethylene even though in the last sections, whenever we were just dealing with ethene, which is a 2-carbon double bond, we called it ethene. As soon as we moved to polymer chemistry, because of the importance and because of how many items were made, and they were made from these things before the IUPAC naming came along, then for the sake of respect, we are going to use the old common names. So the point there is in polymer chemistry, here's ethene, and we all of a sudden are calling it ethylene. They are one and the same. So if we put an ethylene molecule and an ethylene molecule and another ethylene molecule and a whole bunch of them, we're going to get this polyethylene chain. And if you look on the bottom of different plastic items, you might see the abbreviation PE. And guess what PE stands for? It is polyethylene. Notice it's a very long repeating chain. You go, well, how does it happen? Well, actually, the double bond, the electrons from the double bond, one can pair up and form a bond, and another can pair up here, and they connect just by breaking the double bond and connecting the small units together. Polyethylene is made using an addition reaction with the polymer unit ethylene, which is what we just mentioned. And so common uses for polyethylene include plastic bottles, film, insulation, other materials. So here's our polyethylene. Now Teflon, you probably have some Teflon in your house with, you put some Teflon coating on your pans. I don't mean you put it on, but you have it on your pans. And so you go, well, what's Teflon? Well, T from the tetra, because we have 4 fluorine atoms on our basic ethylene unit. So we switch out the hydrogens with fluorine, and hence we then have 4 fluorines. Hence tetra, fluoral, that's the tefla, okay, and Teflon is tetrafluoral. And then the basic unit is our ethylene molecule that has had the hydrogen switched out with fluorine. So if we put a bunch of those together, we get polytetrafluoroethylene, otherwise known as Teflon, which, by the way, I hope you know that if you've got your Teflon all scratched up, that you need to throw away your pan, because it can then flake off, and then it can kind of stay in your body if you eat the food that has it flaked off. So if your Teflon is all scratched up, please toss it away. Now, polypropylene. Okay, so here's our propene molecule. 1, 2, 3 carbons with a double bond. Propene. Well, this old common polymer chemistry, we're going to call it propylene. And if we put many of these units together, we have polypropylene. Polypropylene is used for ski and hiking clothing, carpets, and artificial joints. And if you look on containers or other items and you see the initials PP, PP stands for polypropylene. Now, styrofoam cups, you probably know of styrofoam cups. Well, let's see what styrofoam cups are made with. So here's our basic polymer, which is our ethene, so a carbon and a double bond. But if we switch out one of the hydrogens for the benzene ring, we get the old common name styrene. So all styrene is the ethene that has one of the hydrogens switched out for a benzene molecule. So then if we connect it and make polystyrene, we connect with the double bonds and we'll form connecting groups. So you have your styrene, which has this benzene molecule on it, but we have many of them. It's used for our plastic coffee cups, cartons, insulation. Now, I don't know if you know, but let's say you're out camping. I'm assuming you know not to throw your styrofoam cups in the fire because the vapors are not good. Now you know probably why the vapors are not good. If you're standing over the campfire and you're throwing the styrofoam in, you're breathing in those vapors. Notice what we have on our styrofoam. We have our benzene ring. Now, our PVC, you probably heard of PVC pipe, or you probably have your plastic hose, or you also have your white PVC. So it depends on how they connect these, depending on how strong they want it. But let's see what PVC is. Well, see, first of all, the P stands for poly. Well, let's see what the VC is. Well, so here's our basic ethene molecule that has 2 carbons, a double bond, but let's see what they switched out for a hydrogen. So they put a chlorine, 1 chlorine in the place of a hydrogen. So that's our basic molecule. And the reason why it's vinyl is it's just in the vinyl position, which we haven't talked about that, and we're not going to at this level. Only if you're in the higher level chemistry that they'll talk about the vinyl position. So here is our vinyl chloride. So it's a chlorine on the ethene molecule that's replaced 1 hydrogen. So if we put a whole bunch of these together, we have polyvinyl chloride, i.e. PVC. Now, your saran wrap, or the little thin stuff, another one is 1,1-dichloroethene. And so you'll notice here in this case they replaced 2 hydrogens with 2 chlorines. So name the starting monomer and give it structure for each of the following polymers. So you need to be able to tell us what does the structure for the ethylene look like. What does the structure for PVC look like? Well, the monomer. And what does the monomer for styrene look like? So as you notice here, hopefully you can now draw these. There are many applications for synthetic polymers in clinical medicine, both inside and out of the body, whether it's dialysis, general surgery, orthopedic implants, bone cements, repair of tendons and ligaments, vascular stents. The list goes on, and that's why it's a shame not to be talking and learning a little bit about polymers in our organic chemistry. So as you are working in the health field, you will find out that just everything about whatever they're using is probably something to do with a polymer of some sort.